Welcome! In this session, we'll explore LeetCode problem number 2181, merge nodes in between zeros. This problem involves linked list manipulation, where we merge the values of nodes located between zeros. Stay tuned as we break it down step by step. In this problem, you're working with a singly linked list where the values of the nodes range between 0 and 10 cubed, inclusive. A key detail is that the first and last nodes in the list will always be 0. Your goal is to process this linked list by merging the nodes between every pair of consecutive 0 nodes. For each of these pairs, you calculate the sum of the nodes located between the two zeros. Once you've computed the sum, you replace the first 0 in the pair with this sum, and then remove all the other nodes between the two zeros. This process is repeated for every consecutive pair of 0 nodes in the list. Ultimately, you'll return the modified linked list, where the segments between zeros have been replaced with their corresponding sums. To illustrate this process, let's look at an example. Suppose the input linked list is 0, 3, 1, 0, 4, 5, 2, 0. The first pair of 0 nodes encloses the sublist 3, 1. If we add these values together, the sum is 3 plus 1 equals 4. Next, the second pair of 0 nodes encloses the sublist 4, 5, 2. Summing these values gives 4 plus 5 plus 2 equals 11. After performing the merge operation for all pairs of 0 nodes, the resulting linked list is 4, 11. This demonstrates how each segment of nodes between zeros is replaced by its sum. In another example, consider the input 0, 1, 0, 2, 3, 0, 4, 0. Here, the first pair of 0 nodes encloses 1, so the sum is simply 1. The second pair of 0 nodes encloses 2, 3, and their sum is 2 plus 3 equals 5. Finally, the third pair of 0 nodes encloses 4, with a sum of 4. This means the modified linked list becomes 1, 5, 4. On the other hand, if the input is 0, 0, there are no nodes between the first and last 0 nodes, so the resulting list is empty. This brings us to some important details about the constraints of the problem. First, the linked list will always begin and end with a 0, and it will contain at least one pair of consecutive 0 nodes enclosing some values. The number of nodes in the linked list ranges from 3 to 200,000, and each node's value falls between 0 and 10 cubed. For minimal input, such as 0, 0, the output is an empty list because there are no nodes to sum. For a single segment with a large sum, such as 0, 1000, 1000, 0, the output is 2000, since the sum of the enclosed segment is 1000 plus 1000 equals 2000. Additionally, consider cases where each pair of 0 nodes encloses only one value. For instance, if the input is 0, 7, 0, 8, 0, 9, 0, each segment contains a single node, so the output is 7, 8, 9. Finally, with large input sizes, where the list alternates between 0 and a positive integer up to the limit of 200,000 nodes, the algorithm must efficiently handle these large datasets within the specified constraints. This ensures the solution remains performant even for the upper bounds of the input size. To solve the problem of merging nodes in between zeros in a linked list, we need a strategy to efficiently process the list. The goal is to compute the sum of values between consecutive zeros and construct a new linked list containing these sums. One of the initial approaches we can consider is the brute force method. The intuition here is straightforward: traverse the list while keeping a running total of values between two zeros. Once you encounter another 0, you append this sum to a new linked list, reset the running total, and repeat. The key steps include initializing a new linked list for the results, iterating through the input list while summing values, appending the sum when a 0 is encountered, and skipping the first and last zeros, as they are not part of the result. This approach has a time complexity of O(n), since we traverse the list once, and a space complexity of O(n), as it requires creating a separate linked list to store the results. While the brute force approach is simple and achieves optimal time complexity, it does have a drawback: the additional memory required to create a new linked list. This means the solution is not in place, which can be less efficient if minimizing space usage is important. To address this, we can consider an optimized approach that modifies the input list directly. In this method, instead of creating a new list, we traverse the input list and sum the values between zeros. Once a 0 is encountered, we replace the next node of the last zero boundary with the summed value and remove the intermediate nodes. This approach involves initializing a pointer to traverse the list, maintaining a running sum, and updating the input list in place when a zero is found. By skipping the first zero and eliminating unnecessary nodes between zeros, we streamline the process. The result is a solution with O(n) time complexity and O(1) space complexity, as it does not require any additional data structures. There are several key observations that make the optimized in-place modification approach effective. First, since the first and last nodes are guaranteed to be zeros, we only need to process the intermediate nodes. This allows us to focus on merging values within those boundaries. Additionally, modifying the list in place saves memory and avoids the redundancy of creating a new linked list. This makes the approach not only space efficient but also straightforward to implement iteratively. While alternative approaches exist, such as using recursion or a two-pass method, they come with their own limitations. For example, recursion introduces the risk of stack overflow for large lists and is generally less efficient than iteration. The two-pass approach, where we calculate sums in the first pass and rebuild the list in the second, is simpler but requires extra space for storing sums, making it less optimal than the in-place solution. The optimized in-place modification approach stands out as the most efficient and practical strategy for solving this problem. With a time complexity of O(n) and a space complexity of O(1), it achieves optimal performance. By avoiding additional memory usage for new lists or arrays, it is particularly well suited for scenarios where minimizing memory usage is critical. This approach is also straightforward to implement iteratively, avoiding the complexity or risks associated with recursion or multipass solutions. However, a trade-off to consider is that the input list is modified, which may not be ideal if the original list needs to be preserved. In such cases, the brute force approach may be an alternative, albeit with higher space usage. The key insight here is that intermediate nodes between zeros can be directly replaced with their summed value, eliminating redundancy and simplifying the process. This realization makes the in-place modification strategy the most balanced solution, combining efficiency, memory optimization, and simplicity into a single cohesive approach. In this problem, we are working with a singly linked list where the first and last nodes are guaranteed to be zeros. Our task is to merge the values of all nodes that lie between consecutive zeros and produce a new linked list. Each node in this output list will represent the sum of these values. For example, if the input linked list has segments separated by zeros, we'll calculate the sum within each segment and store it as a single node in the result. Now, because the problem is naturally defined in terms of a linked list, it makes sense to use this data structure. Traversing a linked list is linear in time complexity, and we can accomplish the task without requiring additional storage structures. Some key insights include the guaranteed zero boundaries, which simplify the algorithm since we always know where to start and stop summing values. Furthermore, the sequential traversal of the linked list allows us to calculate sums on the fly, minimizing space usage as we construct the result list directly during the traversal. To implement this algorithm, we start by initializing a few variables. First, we create a dummy node, which acts as the head of our resulting linked list. This dummy node helps simplify edge cases, such as when the result list is empty initially. We also initialize a variable called current_sum to accumulate the values between zeros, and a pointer result_tail to keep track of the last node in the result linked list as we build it. Next, we traverse the input list, starting from the first node after the initial zero. For each node, if its value is non-zero, we add that value to current_sum. When we encounter a zero, it means we've reached the end of a segment. At this point, we create a new node with the accumulated sum and append it to the result list by updating the result_tail pointer. After appending, we reset current_sum to 0 so that we can start accumulating values for the next segment. This approach naturally handles edge cases, such as empty ranges between consecutive zeros, as the accumulated sum for such ranges is 0. Even if there's only one segment between the two outer zeros, the algorithm will handle it seamlessly and produce the correct result. Now, let's look at the actual implementation of the algorithm. We start by defining the listNode class, which represents each node in the linked list. The mergeNodes function begins by creating a dummy node, which serves as the starting point for the result list. We use result_tail to track the last node in the result list and initialize current_sum to 0 for accumulating values. As we traverse the input list, we skip the first 0 node and begin processing from the next node. For each node, if its value is 0, this marks the end of a segment. At this point, we create a new node with the value of current_sum, append it to the result list, and reset current_sum to 0. If the node's value is non-zero, we simply add it to current_sum. This process continues until we've traversed the entire linked list. Finally, we return dummy.next as the head of the new linked list, effectively skipping the dummy node itself. This implementation is both concise and efficient, leveraging the structure of the linked list to compute the desired result directly during traversal. When we analyze the complexity of this algorithm, we find that the time complexity is O(n), where n is the number of nodes in the input linked list. This is because we traverse the list exactly once, processing each node in constant time. The space complexity is O(1), as we don't use any additional data structures for intermediate storage. Instead, we construct the result list in place, appending nodes as we go. The key operations include accumulating values with current_sum, which is efficient, and appending nodes directly to the result list. By skipping zeros and focusing only on the segments in between, we ensure that the algorithm remains concise and avoids unnecessary computations. For edge cases, the algorithm handles lists with only zeros by returning an empty result, and it correctly processes consecutive zeros by appending a node with a value of 0 to the result. This approach is well suited for large inputs, as its linear time complexity ensures scalability. By minimizing auxiliary storage and leveraging the linear structure of linked lists, the solution is both clean and optimal. Here, we begin by defining the listNode class to represent a node in our linked list. Each node has a value and a pointer to the next node. Then, we define the solution class, which contains the mergeNodes method to solve the problem. Inside this method, we first create a dummy node with a value of 0. This dummy node serves as the starting point for our result linked list. We also initialize a pointer, current_result, to track the end of our result list and a variable, current_sum, to accumulate the sum of values between zeros. Next, we skip the initial 0 node in the input list by setting the current pointer to head.next. We then enter a while loop that iterates through the linked list. For each node, we check if its value is 0. If it is, this marks the end of a segment, so we create a new node with the accumulated sum, append it to the result list, and reset current_sum to 0 for the next segment. If the value is not 0, we add it to current_sum. Finally, we move the current pointer to the next node to continue processing the list. Once the loop completes, we return dummy.next, which points to the head of our constructed result linked list. This ensures that the final linked list, containing the sums of values between zeros, is returned as the output. By leveraging the dummy node, we simplify the process of managing the result list and avoid special cases for the head node. This concludes our Python implementation for merging nodes between zeros in a linked list. Here, we start by defining the structure of our singly linked list using the listNode class. Each node in the list stores an integer value and a reference to the next node. The class includes several constructors to handle different initialization scenarios, such as creating an empty node, a node with just a value, or a node with both a value and a reference to another node. Next, we define the mergeNodes method, which accepts the head of a linked list as input. To build the resulting linked list, we create a dummy node initialized with the value 0. A pointer, result pointer, is set to this dummy node to help with constructing the output list. We also initialize a variable, segmentSum, to accumulate the sum of values between zeros. The process begins from the node following the initial 0 in the input list, which is accessed using head.next. The method then enters a while loop that traverses the linked list. For each node, we check if its value is 0. If it is, this indicates the end of a segment. At this point, we create a new node with the accumulated segmentSum and append it to the result list by updating the result pointer. We then reset segmentSum to 0 to prepare for the next segment. If the current node's value is not 0, we add its value to segmentSum. This process ensures that we are summing up all the values between two zeros. After processing the current node, we move to the next node in the list. Once the loop completes and all nodes have been processed, we return dummy.next, which points to the head of our newly constructed list, effectively skipping the initial dummy node. In this example, the input linked list starts with a 0, followed by the sequence of nodes containing values 3, 1, 0, 4, 5, 2, and ends with another 0. The goal is to merge the values between each pair of zeros into their sum and construct a new linked list with these sums. To begin, we initialize a dummy node with a value of 0, set the current_result pointer to the dummy node, and initialize current_sum to 0. We start processing the list from the first non-zero node, which has a value of 3. At this node, since the value is not 0, we add it to current_sum, making current_sum equal to 3. We then move to the next node. Here, the value is 1, which is also not 0, so we add it to current_sum, updating its value to 4. Once again, we move to the next node in the list. Now we encounter a node with a value of 0, which acts as a delimiter. At this point, we create a new node with the value of current_sum, which is 4, and attach it to the next pointer of the current_result node. Then, we move the current_result pointer to this newly created node and reset current_sum to 0, preparing to accumulate values for the next segment. Moving forward, we process the nodes with values 4, 5, and 2 sequentially. For each of these nodes, since their values are non-zero, we add them to current_sum. This updates current_sum incrementally from 4 to 9, and finally to 11. After processing these nodes, we arrive at the final node, which contains a value of 0. Once again, we create a new node with the value of current_sum, now 11, and attach it to the next pointer of current_result. The current_result pointer is moved to this newly created node, current_sum is reset to 0, and since there are no more nodes left, the loop ends. The resulting linked list, starting from dummy.next, contains the values 4, 11. In this example, the input linked list contains only 2 nodes, both with a value of 0. As before, we initialize a dummy node with a value of 0, set current_result to point to the dummy node, and initialize current_sum to 0. However, when we start processing the list, we find that there are no non-zero nodes, as head.next is none. Since there are no values to process, the loop terminates immediately. Therefore, the result is simply the empty linked list represented by dummy.next, which contains no nodes. In this third example, the input linked list starts with a 0, followed by the sequence of nodes with values 7, 0, 8, and ends with another 0. We begin by initializing a dummy node with a value of 0, setting current_result to point to the dummy node, and initializing current_sum to 0. The processing begins with the first non-zero node, which has a value of 7. Since the value is not 0, we add it to current_sum, updating its value to 7, and move to the next node. The next node has a value of 0, signaling the end of the current segment. At this point, we create a new node with the value of current_sum, which is 7, and attach it to the next pointer of current_result. Then, we move the current_result pointer to this new node, reset current_sum to 0, and proceed to the next node in the list. The next node has a value of 8, which is not 0. We add this value to current_sum, updating its value to 8, and move to the final node. This last node contains a value of 0, marking the end of the segment. As before, we create a new node with the value of current_sum, which is 8, and attach it to the next pointer of current_result. We then move current_result to this new node, reset current_sum to 0, and since there are no more nodes to process, the loop ends. The resulting linked list, starting from dummy.next, contains the values 7, 8. The time complexity of our solution is O(n), where n represents the number of nodes in the input linked list. To understand this, let's break it down step by step. First, the algorithm traverses the entire linked list exactly once using a while current loop. During this traversal, each node is visited only one time, and the operations performed at each node, such as checking its value, summing segment values, or creating a new node, are all constant time operations, or O(1). So, the total cost of this traversal is directly proportional to the number of nodes, giving us O(n). Additionally, as we process each segment of nodes between two zero nodes, a new node is created for the output linked list. The number of new nodes created corresponds to the number of segments, which in the worst case could match the number of nodes if there are many zeros with short segments in between. However, since creating each node is an O(1) operation, the overall cost remains dominated by the traversal. Therefore, the total time complexity remains O(n). Now, let's analyze the time complexity across different scenarios. In the best case, the linked list contains only two zero nodes, with all other nodes belonging to a single segment. Even in this scenario, the traversal still takes O(n), because we visit each node once. In the average case, the segments are evenly distributed throughout the list, but again, the traversal cost remains O(n). In the worst case, the list alternates between zero nodes and single non-zero nodes, leading to the maximum possible number of segments. Even with this, the traversal still requires O(n) time, as each node is visited only once. Thus, regardless of the distribution of zeros and segments, the time complexity of the solution is consistently O(n). Turning to space complexity, the solution operates with constant auxiliary space, making it O(1), excluding the input and output. Let's break this down further. The input linked list is processed in place, meaning no additional memory is allocated to store or duplicate it. The output linked list, while it does require space for the new nodes, is not considered auxiliary space since it is part of the result. The space required for these new nodes is proportional to the number of segments, or OK, where K is the number of segments between zero nodes. However, this is part of the output and does not affect auxiliary space. Finally, the algorithm uses a handful of pointers like dummy, current_result, and current, along with a single integer variable current_sum. These require a fixed amount of memory, regardless of the input size, resulting in an auxiliary space complexity of O(1). To put this in perspective, let's compare the current approach with a naive one. A brute force method might involve traversing the linked list multiple times to calculate segment sums or using additional data structures, like arrays, to store intermediate results. This could lead to a time complexity of O(n²) in the worst case, where each segment requires its own traversal, or a space complexity of O(n) if we store intermediate values. In contrast, the current solution is highly efficient. It traverses the input list exactly once, achieving a linear time complexity of O(n). It also constructs the output list with constant auxiliary space, O(1), avoiding the need for additional data structures. Mathematically, for n nodes in the input list, each node contributes O(1) work, leading to a total time complexity of n*O(1), which simplifies to O(n). The auxiliary space usage does not grow with input size, remaining O(1). Therefore, the solution is optimal, balancing both time and space efficiency. This problem often trips up developers because of a few common mistakes that are easy to overlook. First, forgetting to skip the initial and final zeros is a frequent issue. Since the problem guarantees that the first and last nodes are zeros, these should act as boundaries rather than contributing to the sums. Including them would lead to incorrect calculations and invalid output. Another common pitfall is not handling edge cases effectively, especially when dealing with small inputs. For instance, with a minimal input like 0, 3, 5, 0, it's crucial to ensure the logic doesn't assume multiple zero-separated segments, as this could unnecessarily complicate your solution. Lastly, modifying the linked list structure while iterating is another common misstep. If you remove or skip nodes during traversal without careful planning, it can lead to skipped nodes or even infinite loops, making the solution unreliable. Properly managing these aspects is critical for a robust implementation. Another mistake to watch for is creating unnecessary new nodes. Some solutions attempt to construct a completely new linked list, but this increases memory usage and complexity. Instead, the problem can be solved more efficiently in place by reusing the existing nodes. Additionally, you should ensure that the sum is properly reset after processing each segment. If the sum is not reset, it could accumulate across segments or cause duplication of results. For example, if you process one segment and then start summing the next without resetting, the sums will become inaccurate. Each segment must be treated independently, with its sum initialized to 0 before processing begins. From an interview perspective, this problem is a great opportunity to demonstrate your ability to work with linked lists. At its core, it tests your understanding of traversal patterns, pointer manipulation, and in-place transformations, key concepts that are essential for linked list problems. Another major theme in this problem is identifying boundaries, such as the zeros in this case, and aggregating data within those boundaries. This pattern is common in many linked list and array-based questions. Interviewers may also probe your ability to optimize your solution, such as by using in-place techniques to minimize memory usage. Additionally, you should be prepared to discuss edge cases, like minimal valid inputs, large lists, or cases where there are no intermediate nodes, such as 0, 0. These discussions can set your solution apart and show your readiness to handle real-world scenarios. If you're looking to strengthen your understanding of linked list problems, there are several related problems that can help solidify these concepts. For example, LeetCode 2, add two numbers, involves summing values within a linked list structure, much like this problem. LeetCode 445, add two numbers 2, introduces a similar summation concept but works with numbers represented in reverse order, challenging your understanding of traversal order. LeetCode 92, reverse linked list 2, focuses on modifying sublists within a linked list, which helps develop skills in boundary handling and partial transformations. Finally, LeetCode 328, odd-even linked list, emphasizes rearranging nodes based on specific criteria, which is a useful exercise in mastering reordering techniques. Working through these problems will deepen your grasp of linked list manipulation and prepare you for a variety of scenarios. There are several alternative approaches to solving this problem, each with its own trade-offs. An in-place modification approach involves traversing the list while summing values between zeros. As you process each segment, you update the current node's value to the calculated sum and skip over the intermediate nodes. This method is highly space efficient, as it uses O(1) extra space, but it requires careful pointer manipulation to avoid errors. Another option is to use an auxiliary list. Here, you traverse the input list, compute the sums, and store the results in a new linked list. While this approach is easier to implement, it comes with higher memory usage, as it requires O(n) extra space for the new list. Lastly, a recursive approach can be used to process the list segment by segment. While this solution is elegant and concise, it is less efficient due to the overhead of the recursive call stack, which also results in O(n) space complexity. Each approach has its merits, so the choice depends on the problem constraints and interviewer preferences. That wraps up our discussion on LeetCode problem number 2181. We learned about linked list traversal and efficient in-place merging. Remember to practice similar problems to master these techniques. Thank you for watching, and see you in the next tutorial. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!